Molecular polarity. How to determine polarity from the structure of a molecule. If we look at polarity, the whole concept of polarity is that it describes charges within a substance. If anything is polar, it will have charge to it. A polar substance, then, is one which has a positive end and a negative end. If we consider something like a magnet has two poles, a positive pole and a negative pole. In the same way, within a substance, any polar aspect of that substance will have a positive end and a negative end. The positive and negative ends of the substance arise from unequal sharing of electrons throughout that region. So if we have one region which is more heavily dominated by electrons than the other, in terms of the way the electrons should be distributed on the atoms normally, then we will find that we wind up with a positive and negative end as electrons are pulled away from the atoms which they belong to and towards other atoms in the substance. If we look at an electron distribution, then, the distribution of the electrons will depend upon the relative electronegativities of the different atoms in the substance. The higher the electronegativity of the atom, the more it will attract electrons to it, and thus the highest electronegativity attracts electrons the most. A difference in electronegativity, where we have difference between the two atoms, can cause electrons' concentration on the substance to differ from one point to another. There are two different types that we deal with. We have bond polarity, where there is a positive and a negative end to a bond between two atoms. And then we have molecular polarity, where an overall molecule has a positive and negative end to it. We don't consider polarity on ionic substances because ions are simply charged atoms that are independent, and they don't function together as a molecule. Therefore, we have either a positive ion or a negative ion. We don't wind up with polarity to the ion. Now, bond polarity is caused by differences in electronegativity between the two atoms which make up the chemical bond. We calculate it by taking the larger electronegativity and subtracting the smaller electronegativity. The negative end of the bond will point toward the atom which has the higher electronegativity. The positive end will point towards the atom with the lower electronegativity. For example, HF has polarity to it, the bond between hydrogen and fluorine. Fluorine is 4.0 and hydrogen is 2.1 on the electronegativity scale. The difference is 1.9. This is going to cause a polar bond where the negative end points towards fluorine and the positive end points towards hydrogen. So fluorine is favored over hydrogen, giving hydrogen the positive side and fluorine the negative side. Now, the nature of the bond depends upon the difference in electronegativity itself, numerically speaking. If that difference is less than or equal to 0.5, we consider it to be a non-polar covalent bond. If it is between 0.5 and 2.0, not inclusive, we consider it a polar covalent bond. And if it is greater than 2.0 or equal to 2.0, we call it an ionic bond. Now, molecular polarity is symmetry dependent. It depends upon the symmetry of the atoms and the electrons within the entire molecule, based upon the particular central atom we're looking at. Ionic atoms are not considered. However, for the molecule, it will depend upon how electrons are pulled one way or another within the molecule. The higher the electron concentration we have, the more polar it is. So if one region of the molecule has a higher electron concentration than another region versus the starting points of the atoms, we're going to wind up with a polar molecule. Equal electron concentrations will produce a nonpolar molecule. The distribution of electrons in a molecule winds up being based upon the molecule symmetry in terms of the lone pairs on the central atom, as well as the nature of the bonds that are connected to that central atom. So we consider non-bonding pairs versus bonding pairs, and polar bonds versus nonpolar bonds. Looking at the differing polarities in polar bonds, if we have two polar bonds which have different polarities to them, in other words, the electronegativity difference of the bonds are different, so one might be 1.0 as a difference, one might be 1.5 as a difference, that will also produce a situation where the two are not equal. We generally will use the geometry-based model like VACPR to explore this polarity idea. In conducting symmetry analysis to look at polarity, we consider first the lone pairs on the molecule. Lone pairs will always be more polar than bonding pairs. So if there's only one lone pair in the molecule, we consider the molecule to be asymmetric because there's no way to compensate for it. If we think of a polarity like a tug of war between 2 points in the molecule, a lone pair will always be dominant and will always win the tug of war. There's nothing else which can pull as strongly as the lone pair can. So if I look at the ammonia molecule, we have one lone pair pointing up and 3 hydrogens pointing down. The 3 hydrogens are all equal to one another, pulling down and to the left towards us and then down towards the right. Overall, we wind up with a negative region on top and a positive region on bottom, which causes a polarity to the molecule, with the negative area of the molecule being that top, represented by the head of the arrow, which I've colored blue, and the positive area towards the bottom of the arrow where the hydrogens are, which is colored red. However, if I have 2 or more lone pairs, the symmetry of the molecule depends upon the orientation of those lone pairs. If we look at the molecule for water, we have 2 lone pairs, and considering the way the electrons are being pulled, they're being pulled from hydrogen towards oxygen in both cases here. So we have the positive end of the polar hydrogen-oxygen bond pointing towards hydrogen, the negative end towards oxygen. But looking at oxygen versus the lone pair, in both cases, the negative end is pointing towards the lone pair, pulled away from the oxygen. So you can consider the electrons as flowing from hydrogen all the way up towards the lone pair. They're all being pulled up towards the lone pair. And notice that the 2 lone pairs are not directly against one another. They're one pointing up and one pointing to the right, which has a net result of pointing to the top right. If I look at the way that the electronegativity or the polarity distribution is, we have a negative region up towards the lone pair and a positive region down towards the hydrogen. So we have a polarity oriented towards the top right-hand side of the molecule, again with the negative blue region on the top right, the positive red region on the bottom left. But if I consider the molecule xenon tetrafluoride, we have 4 fluorines and 2 lone pairs. The 2 lone pairs are directly opposed to one another in a tug of war, one pulling straight up and one pulling straight down. We can consider the 4 fluorines to be the 4 sides of a square, or the 4 corners of a square rather, and so those corners all pull directly against one another. And since the fluorine-xenon bond is the same polarity for all 4 fluorines, none of the 4 fluorines wins the tug of war against any of the other 4. Neither do the 2 lone pairs win the tug of war against one another. So nowhere in this molecule is there a region with more electrons than another is, pulled away from their starting atoms. And so this winds up being a nonpolar or a symmetric molecule. So if the lone pairs are symmetric, or there are no lone pairs, then I have to look at the bonding configuration. So looking at bonds, if all of the bonds are nonpolar, I've already looked at lone pairs. I've determined I can't determine the total polarity from the lone pairs. I've moved on to bonds. If they're all nonpolar bonds, the molecule will be symmetric because there's no way for one region to be more polar than another if there is no polarity to the bond itself. If I look at something like methane here, all of the hydrogens are pointing towards carbon, but they're all pointing equally away from one another. If there is one or more polar bond, though, then the symmetry of the bonds determines the polarity of the molecule. If the difference in electronegativity is equal in all directions, then the molecule will wind up being symmetric. If I look at this carbon tetrafluoride, even though all of the fluorines are having electrons pulled towards them, they're all pulling opposite one another. The 3 on the bottom are opposed to the 1 on the top, and the 3 on the bottom are all pulling equally with each other. So none of them gains an advantage over another fluorine. Therefore, no point in the molecule is pulled more than another, so it's overall symmetric. However, if the difference in electronegativity is not equal everywhere, then we have an asymmetric molecule. Consider this: if I replace one fluorine with a hydrogen, now the fluorines are all pulling towards the fluorine, the hydrogen's pointing towards carbon. So overall, we think of the electrons as moving down towards fluorine from hydrogen. This produces a situation where the polarity points down towards the fluorines, with the negative end at the fluorine and the positive end at the hydrogen. If I flip it, and I have 3 hydrogens on bottom and 1 fluorine on top, then it's the same situation, moving from the hydrogens towards carbon and from the carbon towards fluorine, so they're all flowing up towards the single fluorine. And we have the opposite direction of our polarity, with the negative pointing up and the positive pointing down. So the symmetry of the molecule determines its polarity. If the molecule is completely symmetric, it is going to be nonpolar. However, if it is asymmetric, because of either lone pairs or bonds, it will be polar. So in summary then, we first look at the lone pairs. If there is only one lone pair on the central atom, it will be an asymmetric molecule, which will be polar. If there are 2 or more, then it depends on the orientation of the lone pairs. If the lone pairs are symmetric to one another, then we have to look at the bonds. So we have to determine polarity by looking at bonds. However, if they are asymmetric to one another, then the molecule is asymmetric overall and is polar. Looking at the bonds, if all of the bonds are going to be nonpolar bonds, we've already looked at there are either no lone pairs or they are symmetric lone pairs. All nonpolar bonds will create a symmetric molecule, which will be nonpolar. If any of the bonds are polar, if the difference in electronegativity is equal in all directions, it will be a symmetric molecule, which will be nonpolar. But if the difference in electronegativity is not equal everywhere, it will be asymmetric, which will be polar. So in the end then, the point to take away is a symmetric molecule will be nonpolar. An asymmetric molecule will be polar. And this does sound backwards because we think of the term A in front of symmetric being not, non in front of polar being not polar, so the two nots don't match with one another. The non-polar matches with symmetric, the asymmetric matches with polar, which is a point one has to keep in mind.